Okay, we're continuing with Chapter 4 in the chemistry textbook. Chapter 4 on reactions in aqueous solutions. In this video, we're going to go through section 4.5, which talks about concentration of solutions. So, okay, to study solution stoichiometry, we must know how much of the reactants are present in a solution and also how to control the amounts of reactants used to bring about a reaction in aqueous solution. So, okay, what is a solution? Let's remind ourselves on what exactly a solution is. We talked about the definition of a solution in Chapter 1, right? So remember the different ways in which all matter is classified. You've got substances. A substance is either going to be an elemental form of a substance or a compound. A compound is a substance composed of two or more different types of elements. And a substance is just a pure chemical form of matter. A substance, you can write its composition with a single chemical formula, like H2O2. Okay, and so any matter in the universe is either going to be a substance, so a pure chemical form that you can represent the composition of that matter with a single chemical formula, or the matter is going to be a mixture, which is a mixture of two or more substances. Okay, and there were two types of mixtures, homogeneous and heterogeneous mixtures. The difference between a homogeneous and heterogeneous mixture is that a homogeneous mixture is thoroughly and uniformly mixed. Meaning, so, okay, with any mixture, you've got the single component of all of the substances that's present in the largest amount, and then you think about how all of the other substances present in the smaller amount are mixed into the larger substance. And so in a homogeneous mixture, the idea is the concentration of the substances present in the smaller amount is the same throughout the mixture. This wouldn't be the case in a heterogeneous mixture like granite, for example. You could inspect different points and you can see some of these regions are a little bit lighter overall. Some are a little bit darker overall. Okay, but more specifically, from a physical standpoint, what we learned is that in most cases, a homogeneous mixture is created when the substances present in the smaller amount dissolve into the substance present in the larger amount. This doesn't always have to be the case, so dissolving doesn't always have to take place to create a homogeneous mixture. For example, when different gases mix together, like oxygen, nitrogen, and argon gases present in air, the mixing process isn't a dissolving process, it's diffusion, but still, air is definitely a homogeneous mixture of multiple gases. Okay, but most of the time, a homogeneous mixture is created via the dissolving of the substances present in the smaller amount into the substance present in the larger amount. Okay, and then also remember that substances can dissolve into, say, water, for example, without breaking up into ions. So sugar, C12H22O11, is soluble in water, but the entire molecules just get dissolved. There's no breaking up into ions. Sugar is not an electrolyte. Okay, and so now homogeneous mixtures are also known as solutions. Solution, the term solution is another name for a homogeneous mixture. And the terms solute and solvent are used to describe the components of a solution. Not any mixture, so the terms solute and solvent don't apply to a heterogeneous mixture, only to a homogeneous mixture or a solution. Okay, and so in a solution, the solvent is the substance present in the largest amount. And note that there can only be one solvent in a solution. The solvent does the dissolving. Okay, and then the solute or solutes are the substance or substances present in the smaller amounts in a solution. The solutes get dissolved if dissolving does take place. And so you can notice that there can be multiple solutes, one or more solutes. Okay, now also remember that there are different types of solutions. We most commonly think of a solid liquid solution, but there's solid solutions. Like steel, right? It is a solid solution of carbon and iron. Air is a gas solution. Carbonated water is a gas liquid solution. Okay, and so now, again, it says to study solution stoichiometry, we must know how much of the reactants are present in a solution and also how to control the amounts of reactants used to bring about a reaction in aqueous solution. All right, so they're talking about solution stoichiometry here. Okay, so if you think about it, we haven't done any stoichiometry so far in this chapter with the reactions we've studied, specifically the reactions in aqueous solution. So forgetting about some of the redox reactions we looked at that weren't in solution. So for the precipitation, acid, base, and redox reactions that took place in aqueous solution, we never did any stoichiometry, right? And so that's what they're talking about here. If we want to do stoichiometry with a chemical reaction that takes place in solution, so we're talking about reactions in aqueous solution in this chapter, but this same idea would apply to a reaction taking place in any kind of solution. Okay, so if we want to do stoichiometry with a chemical reaction that takes place in solution, then we have to have a way of communicating amounts of reactant or product species present in relation to solutions, right? And so that's what this section is talking about. So the concentration of a solution is the amount of solute present in a given amount of solvent or a given amount of solution. Okay, so this definition is saying that it says the amount of solute present. It just says not solute plural because we would think about the concentration of individual solutes. If there's multiple solutes in a solution, then you would have a concentration of each solute. So the amount of a specific solute present in a given amount of solvent or a given amount of solution. So why are they implying that the amount of solvent and the amount of solution are pretty much the same thing? Well, because in general, that's going to be the case. When you have a glass of water and you dissolve some salt into the water, the overall solution volume is just the same as whatever the volume of the initial solvent was, right? I mean, if you were trying to be extremely precise, then maybe you would have to, I mean, obviously to some degree, the solution will get larger once solute is dissolved. And so depending on the type of problem you're working, you might have to consider the actual change in volume once a solute or solutes is added to a solvent. But in general, for many problems, this difference in volume is negligible. Okay, so it says, for this discussion, we will assume the solute is a liquid or a solid and the solvent is a liquid. Okay, yeah, so we're about to talk about, let's just think about the solvent being a liquid, like aqueous solution would be, right, where the solvent is water, liquid water. Okay, the concentration of a solution, of a specific solute dissolved in solution, a liquid solution, can be expressed in many different ways, as we will see in chapter 12. Okay, but right now we just consider one of the most commonly used units in chemistry, molarity, or molar concentration, which is the number of moles of solute per liter of solution. Okay, so again, to express the amount of a species, of a substance present in a solution, one of the most commonly used units is molarity. To where you're referring to one of the solutes, the concentration of one of the solutes. And remember, a solute is going to be a pure substance, elemental form or a compound in this mixture, this homogeneous mixture. So with respect to one of the solutes, the molarity of that solute in the solution, which is an expression of the amount of that solute in the solution, is given by, so the total number of moles of solute present, there's the amount, divided by the total volume of the solution. Okay, and then algebraically, molarity is expressed like shown here, N divided by V. Number of moles of a specific solute divided by the volume of the solution. So a 1.46 molar glucose solution, written as, so 1.46 molarity of glucose contains, what is this saying? That this contains 1.46 moles of these molecules. That count of these molecules, remember moles is a count, so 1.46 times 6.022 times 10 to the 23rd of these molecules dissolved in 1 liters of whatever solute this is in reference to, right? So like the term molarity can be in reference to any solvent you want, liters of whatever the solvent is. Okay, but of course we do not always work with solution volumes of 1 liter. Thus, okay, if we were referring to this, we had a 1.46 molarity glucose solution, but it wasn't 1 liter of solution, it was 500 milliliters of this solution. Well, then okay, in that case, we would have to say, well, convert this to liters, so 0.5 liters, and multiply that by the molarity, and then you'll know the count of these in moles of these molecules in that solution. And that's what they do here. So, well, they actually say, yeah, they had to cross multiply. If you do 0.5 times 1.46, you're going to get 0.73. But they just indicated that, okay, if we let's say we had 0.73 moles of glucose molecules, divide that by 500 milliliter solution, but convert that to liters, then that's the correct molarity. So in both of these solutions, in 1 liter and 500 milliliters of this solvent, you had the same concentration, but since there was the total solution volume was less here, then to have that same concentration, you needed less moles of the solute, right? Or else the concentration would have gone up. It's like salt water. If you dissolve a certain amount of salt in a certain amount of water, a certain amount of salt in, say, a gallon of water versus that same amount of salt in a liter of water, it's going to be much more salty, meaning a higher concentration of salt in the smaller volume for the same amount of salt dissolved. And so here to maintain the same concentration, you went from 1.46 moles in 1 liter of glucose to 0.73 moles in 500 milliliters, so that the concentration wouldn't change. Okay, note that concentration, like density, is an intensive property, so its value does not depend on how much of the solution is present. Yeah, exactly. The density of steel, steel has the same density regardless of if you're holding a steel ruler in your hand or you're looking at a big steel cross beam. They both have the same density. It's the same idea with concentration. Concentration is normalized with respect to the amount of the solution, just like density is normalized with respect to the volume of steel. Okay, it is important to keep in mind that molarity refers only to the amount of solute originally dissolved in water and does not take into account any subsequent processes, such as the dissociation of a salt or the ionization of an acid. Yeah, so this is really important. If you're referring to the molarity of a solute, so the molarity of hydrochloric acid, the molarity of sodium hydroxide, the molarity of sugar in a solution, dissolved in a certain solution, that molarity it's referring to the whole entire molecule or unit of that substance. There's no statement being made about what happens after that substance is dissolved in the solution. Like an ionic compound, for example. So consider what happens when a sample of potassium chloride is dissolved in enough water to make a 1 molarity solution. So what this is saying is that 1 molarity, you've got 1 mole of potassium chloride units that count per liter of the solution, whatever the solution is, presumably, water. You've got 1 mole of these potassium chloride pairs. Even though we know that as a soluble ionic compound, this potassium chloride actually breaks up into ions like this. And so you could also then, for this case, make a statement like, okay, so it says, in this case, since potassium chloride is a strong electrolyte, so it undergoes a complete dissociation in solution. If it was a weak electrolyte, we couldn't state what we're about to state. So because it's a strong electrolyte, then we can say that, and because you can assume we didn't exceed the solubility of the solution either, in which case there would some of this solid would not dissolve. But assuming we didn't exceed the solubility or the saturation point, then since this is a strong electrolyte, we can assume all or a very large percentage, with whatever's not dissolved being negligible, of these KCl Cl units disassociated. And so we could then make a statement then that the concentration of K plus ions in the solution is 1 molarity, and the concentration of Cl minus ions in the solution is 1 molarity as well. There's 1 mole of K plus ions per liter of solution. There's 1 mole of Cl minus ions per liter of solution. And if we wanted to make a statement of how many total ions are in the solution, well, then it would be 2 molarity because there's 2 moles of ions per liter of solution, right? But again, when just referring to what was originally dissolved in the solution, okay, so it says that the concentration of the ions can be expressed as the concentration of K plus ions is 1 molarity, and the concentration of Cl minus ions is 1 molarity, where the square brackets indicate that the concentration is expressed in molarity. So yeah, when you use square brackets like this around an ion or a compound, you're saying that represents the concentration of that ion or compound, but in molarity. This is indicating the molar concentration. That's what square brackets are used for in chemistry. Similarly, in a 1 molarity barium nitrate solution, this soluble ionic compound disassociates into ions, but this is a little bit different in that we've got, since this is BaNO3, the dissociation is for every 1 barium nitrate unit, it's going to dissociate into a Ba2 plus ion and 2 NO3 minus ions. And so what you've got is the resulting concentration of barium 2 plus ions is 1 molarity, and the concentration of NO3 minus ions is 2 molarity. But then the total concentration of ions in general would be 3 molarity, right? Because you had 1 mole of these dissolved in a liter of solution. But for every one of these, you have 3 ions came out. So in total, there's 3 moles of ions in this, but the same liter, that same 1 liter of solution, or per whatever the solvent concentration is. Regardless, they're saying there's 1 mole of these per whatever the initial concentration is of the solvent or the solution. So now this breaks up to where we have 3 moles of ions, and so 3 moles per whatever the solution volume is, so the concentration of ions is 3 molarity. Okay, the procedure for preparing a solution of known molarity is as follows. First, the solute is accurately weighed and transferred to a volumetric flask through a funnel, like shown here. So the solute or solutes, you would accurately weigh the mass and add it into an empty flask. And you could note how with the mass of the solute, you could easily use molar mass to get the moles of the solute, right? So you have this empty flask with all of your solutes with their known masses that you accurately weighed. Okay, then next, water is added to the flask, which is carefully swirled to dissolve the solid. So you just add some water to the flask, not a lot, but just enough to like disperse the solutes, and then swirl the solution around, the mixture around, to allow everything to dissolve. Then after all the solids have dissolved, then you go ahead and add more water slowly to bring the level of the solution to the volume you're looking for, right? Because but beforehand, you know what molarity you're looking for. You know what concentration you're looking for. And then you either know, you're going to specify beforehand what volume you want, volume of solution you want, or you're specifying beforehand what mass of the mass of the solutes is going to be, depending on the problem. So that you could easily use this formula here to solve for whatever the resulting volume needs to be, or whatever the resulting number of moles of the solutes needs to be, which you could easily determine. And so then coming into this, you already know what the final volume is going to be. You have it marked off. And you know what the mass of the solutes needs to be. So you add the solutes in first. You add some water, and a little bit of water just to submerge the solutes, and then you swirl that mixture around to dissolve the solutes. Then you add more water to the final volume mark, right? Because again, just to be clear, coming in, but before you start this procedure, you already know that this mass of solute, if you convert that to moles, however many moles that is, divided by this volume of solution is the concentration you want. You already know that coming in. So they're just saying this is how you prepare it. Okay? Now, next, they talk about the dilution of solutions. So it says concentrated solutions are often stored in the laboratory stockroom for use as needed. So the common practice is you'll make these highly concentrated solutions, and then, like it says, store them in the stockroom, and then when you need to use that type of solution, then what you do is you use that highly concentrated solution to create a more diluted solution. So dilution is the procedure for preparing a less concentrated solution from a more concentrated one. And the idea of how you do this, it goes through an example here, but I think it's easier just to come to the final formula. So the whole idea is that you're going to know what concentration of solution you're wanting to obtain, right? That's the whole idea. You're saying that, okay, let's say there's this 10 molarity concentration hydrochloric acid solution that's stocked in the stockroom, and you want to get a sample, a beaker of a 1 molarity hydrochloric acid solution. You're going to know that, right? Okay, and so the big idea of how to understand this dilution process is that, so like what you're going to do is you're going to take out a certain volume of the highly concentrated solution and put it into a beaker. Then you're going to add more of the pure solvent to that concentrated solution, however much you need to get the diluted concentration you're looking for, right? You might take out 2 liters of the highly concentrated hydrochloric acid solution, and then the plan is to add 5 liters of pure water to that solution to get to get the 1 molarity hydrochloric acid solution you're looking for. And so but the key point to realize about this dilution process is that the number of moles before the dilution, the number of moles of the solute before the dilution, is equal to the number of moles of the solute after the dilution, right? You added the 2 liters of the 10 molarity hydrochloric acid to a beaker. Well, there's a certain number of moles of that hydrochloric acid in the beaker, right, at that moment. But then once you go through the dilution process, you're adding more pure water to that solution. You're not changing the number of moles of the hydrochloric acid, right? That's what they're showing here. You're starting off with this highly concentrated solution. You add more of the pure solvent. Well, the number of moles of the solute isn't changing. And that's the key to understanding dilution. Because the number of moles of the solute isn't changing, then if we think about the formula for molarity, well, since N is constant, if we cross multiply, the number of moles is equal to M times V. Well, since in this particular process, this dilution process, going from here to here, N doesn't change. N is a constant. What that means is that M1 V1, the molarity times the volume of the highly concentrated solution, is equal to the molarity times the volume of the diluted solution. And so with this relation here, again, you're thinking about going from this step to this step. You can choose to start with any volume of highly concentrated solution you want. Okay, and then with that, you know what the concentration of the highly concentrated solution is, right? And then here, you know what concentration you're looking for. The question is, how much of the solvent do you add here? That's the big question. Well, you can figure that out because you know this information and because you're choosing this and you're choosing this. Okay, so that's how the dilution of a solution works. Now that we have discussed the concentration and dilution of solutions, we can examine the quantitative aspects of reactions in aqueous solution, or solution stoichiometry. So the upcoming sections focus on 2 techniques for studying solution stoichiometry: gravimetric analysis, and titration. These techniques are important tools of quantitative analysis, which is the determination of the amount or concentration of a substance in a sample. And so that's what we're going to look at in the next video.